This presentation is delivered by the Stanford Center for Professional Development.
What we're doing today is actually just looking at some extremely useful extensions of least squares. And many of them involve this idea of multi-objective least squares. So in multi-objective least squares, instead of having just one objective like ax minus y, norm squared, that you want small, there are actually two. And so you want them simultaneously small. Now, one of the problems there is the semantics of that is not clear. So it doesn't really make any sense to say, oh yeah, please minimize these two things. It makes absolutely no sense. I mean, so the first thing you have to work out is what is the semantics. And by the way, if they're not competing, it does make sense, but that's an extremely rare case. So otherwise, you have to figure out what even does it mean to minimize two objectives. So we started looking at that last time, and as a thought experiment, we did the following. We simply took every x in Rn, and we evaluated J1 and J2, the two objectives. Now you want both small. And we simply, for every x, we simply put a point. So all the shaded region shows you pairs, as we've written it, J2 comma J1, which are achievable. And then the clear area here are pairs that are not achievable. So we talked about this last time. We talked about the following idea, that if you take if a certain x corresponds to this point, then basically all the x's corresponding that map into what is lower and to the left, lower left, these are actually points that are unambiguously better than this one. Everything up and to the right, that is unambiguously worse. And unambiguously better or worse means that on both objectives it's better. Now the interesting part are the second and fourth quadrants, because here it's ambiguous. And in fact, this is where we're going to have to actually really work out what the semantics is. Here, a point, if you want to compare a point here and here, in fact, one of the ways you'd say this is you'd say that in fact these 2 points are not comparable. One has better J1, but worse J2. The other has better J2, but worse J1. So they're incomparable, is what you say. Okay. Now, the boundary here, which is called the Pareto optimal, these are Pareto optimal points. This is the Pareto boundary, and it's also called the optimal trade-off curve. These points are characterized in the following way. Any point on here, there's no other point that's better. So that's what it means. It means, so what the least you can say, and in fact, actually, to tell you the truth, that's all you can say. If someone says you have a multi-objective problem, you want J1 and J2 small, and they're not yet willing to commit to how you trade off one and the other. So if they simply say, no, I want both objectives small, you can already say something of substance. You can say the following. You can say that that point is a stupid choice. That's for sure. Why? Because all of these are better. You can say that's an attractive choice, but can't be done. Okay? So if someone wants to minimize these two objectives, the only non-stupid choice and non-stupid and feasible choice are going to be the points on this boundary. That's actually, you've already done a lot to say that you can focus your effort on these points on this optimal trade-off curve. Okay. So that's the basic idea in this, and this extends to multiple, 3 objectives, 4, and so on and so forth. Okay, and it's an idea that's completely obvious and that you probably already have in your head anyway. Okay, now there's a very common method to find points on that curve, and it works something like this. Actually, before we even do that, I want to talk about what the curve might look like qualitatively. So let's actually talk about that. And let me try to do this consistently. I'll draw my first objective there and my second here. Okay? So this is what it looks like. That trade-off curve can have lots of different looks. Okay? So I'm going to draw a couple of them. One would be something like this. Like that. Of course, it actually has to go down. So these are all achievable. Something like that. Now that's actually quite interesting. Here, I'll make this 3, and I'll make this 1 to whatever. It doesn't matter. Something like that. Okay? This is very, very interesting. In fact, if you work out that this is the trade-off curve, and actually you'll see how to do that very, very soon. You'll figure out you'll see how to do this. This has huge meaning and implication for this problem. So the way you would describe this sort of casually or informally is this. Basically, you would say there isn't much of a trade-off, right? Because the lowest you could ever get J1 might be over here, and that might be like 0.9. That'd be the lowest value you could get J1, ignoring J2. And it might be here. I mean, this might have an asymptote or something. And this might be 2.6. So here you'd say the smallest you could ever make J2, ignoring J1, taking it absolutely not into consideration, is 2.6. On the other hand, look at this. There's these points right around here which give up, 10% in each objective and yet get both. You see what I'm saying here? So this is, and there's lots, I mean, this is so obvious that, I almost hate to go over this. So this is the proverbial knee of the curve. It's an efficient point. By the way, these ideas are extremely important to have because I guarantee you will be working on problems. You will finish something, you will do something, and the point you will find will be right here. That's what's going to happen. So, my opinion is it's not good enough to simply return that point. It's not responsible. The correct thing to do is to say, oh, yeah, I got J1 down to 0.9. Let's say it's ride quality. It doesn't really matter what it is. Say, I got the ride quality down to 0.9. And they'd say, that's great. You'd say, but you know what? This is when you go back and there's a design review. You say, you know what, though? It turns out, if we accept a ride quality of 1, I can do it with like 1/4 the fuel. That would be, I think it's actually, if you don't point out that there's this point here, I think you're actually being irresponsible. And the same goes for over here. If someone says, find me a point, and you find this point, and you say, I mean, it'd be like if you're doing circuit design. You could say, oh, I can make that thing clock at 2.6 gigahertz. Oh, absolutely. But actually, if it clocks at 2.45, I'll use 1/2 the power. Now, as to whether or not which is the best choice, it depends. But the point is, to me, it's irresponsible if you don't point this fact out. Okay? So basically, you don't ever even do, when you do least squares and things like that, anything involving this. You should always, just as a matter of responsible engineering, you will do studies like this just to check. You wiggle things around to see if things could dramatically change things. Now, the other extreme, so this is one where there's essentially no trade-off. I mean, to really get no trade-off, you do this. That's absolutely no trade-off. This point, actually now it's great. This is the one case where you can say that is the optimal point, period. That's the only time when a bi-objective or multi-objective problem has a unique, well-defined answer where the semantics is clear. That point is good. It's the best one. No other point would be reasonable here. Any other point would be worse than that one that you can achieve. So that's the picture. And this is when there's absolutely no trade-off. Now, let's look at the other extreme. The other extreme happens, and the other extreme looks like this. The other extreme is this. You have a point there and a point there, and this might look something like that. That might be the trade-off curve. Okay? Right. Something like that. Now there's a trade-off. And in fact, this is the opposite. Now the trade-off is actually almost linear in the sense that you can, when you give up one, you actually gain in the other by a fixed amount. Everybody see how this works? And now you have, so this is what people call a strong trade-off. And the slope actually is, I mean, one of the slang names for the slope is the exchange rate. You're actually exchanging J1 for J2 when you move here. When you actually go from this design to this design, let's see, what have you done? You're doing something like you're exchanging J2 for J1. You're doing better on J1 by giving up on J2. And the slope literally is sometimes called, on the streets, it's the exchange rate. Okay? So these are useful just as conceptual models. We're going to leave them up here and we're going to come back to them. Let's look at this idea of the weighted sum objective. which, by the way, comes up independent of discussion of trade-off curves and things like that. It's also completely normal if you have two objectives to, if you want to come up with some answer, to actually just add them with some weight function, with some weight in between them. So I add this function plus mu, this objective plus mu times that one. And the idea is that mu is supposed to give a relative weight between J1 and J2. Is there a question? Great question. So, all right. I was trying to go real fast and kind of avoid that question. So, okay, I'll do it. Could the optimal trade-off curve look like that? That's your question? More or less? Okay. Or you want me to draw it in like that? But okay, that's it. It cannot. It actually has to be convex here. It has to curve up, and that's because for least squares problems, the J1 and J2 are both convex functions. I mean, that's not part of this class. So I was drawing them the way they must look in 263. If you have non-convex functions, they can absolutely look like that. But I will show you one that they cannot look like. It cannot look like this, ever. So it can't look like this. That's not possible, right? First of all, these points are not Pareto optimal because if that's a feasible design, everything above and to the right of this point has a technical, the technical name is it's a bad design, a bad choice, and that means that this is not part of the trade-off curve. So in this case, the trade-off curve for something that would look like that actually is discontinuous. It's got this point, and then it's got this line segment. So these things can happen in the general case with general objectives. They can't happen with quadratic objectives like you'll see in 263. To answer your question? Okay, great. Let's so if you form a weighted sum objective, it turns out you can interpret this easily on a J1 J2 plot or J2 J1 plot, and that's this way. Once I fixed, if I look at level curves of this composite objective, that's J1 plus mu J2. In the J2 J1 plane, these are nothing but lines with slope minus mu. And if you were to minimize J1 plus mu J2, here's what you're doing. You are doing nothing but this. You're moving this line with a slope of minus alpha, which is fixed, and you simply move it down until you last have contact with the set of achievable points. Okay? Now, that is always a point on the Pareto optimal curve. And actually, there's a lot more interesting stuff about that point. Another one is this. If you were to zoom in locally, the local slope here would be exactly mu. So let me summarize that. By minimizing J1 plus mu J2, you will actually find a point on this trade-off curve. That's fact number one. Number two, you will find a point where the local exchange rate is exactly mu, or where the angle is mu. Okay? And you can, by the way, this picture, though simple, explains everything. If I increase mu, what happens? If you increase mu, here's what, well, let's think about what happens. If I increase mu, what you're really saying is, you know what, I care more about J2 than I said before. Okay? So presumably, we'll find a new point where J2 is smaller. Now, you're going to pay for that. J1 is going to go up. Okay? That's the way these things work. So you're going to, so let's just see if you can get that visually. It's very simple. If you crank mu up, that's the weight, you simply change the slope like that. And you do the same experiment. You take this thing and you move it until it just touches, and sure enough, that's the new point for the new slope. Here I cranked up mu by a factor of 3 or something. Okay? And then that's the new point. And sure enough, it's a new point on the optimal curve, and indeed it has reduced J2, and to pay for that, it has increased J1. Everybody see this? So if you can if you have the ability to minimize a weighted sum of the objectives, you can actually now sweep out the optimal trade-off curve by simply sweeping mu over some range and minimizing this weighted sum objective. And you will get points on the you will sweep out points. Now, by the way, if the mu's you choose are not over a big enough range, you will sweep out just a little tiny thing. And in fact, in practice, a lot of people use mu on a log scale because it has to go over usually a pretty big range. But this is just a practical detail. Conceptually, you simply solve this problem for lots of values of mu's, store the design and the J2, J1 achieved, plot that, you have the optimal trade-off curve. And then that's exactly how these curves were created. Okay? But not only that, the picture gives you a lot of geometric intuition about what happens when you mess with mu. And now, I want to go back to my two trade-offs. Here's the problem. There is no trade-off. We can do the one where, let's do the one where there's a slight but very small trade-off. Let's do that one first. So, J2, J1, and I'm going to put a slight but small trade-off, like that. And now, let's talk about minimizing J1 plus mu J2. Okay? Now, what will happen when I minimize J1 plus mu J2? And as I vary mu, what happens? Well, I mean, when you fix mu, you get a slope like this, and you simply march down this thing until you first lose contact with it, and you get a point there. Now you change mu a lot, like that, and you go down here, and you get a new point. And what you should see here is that, in fact, the x's are not changing much. Everybody see that? You're always getting, over a huge range of mu, you're getting points right around there. In other words, you're getting the knee of the curve over some huge range of mu's. Everybody see this? So the two things, here's what you'll notice. Number one, the actual design you get is largely insensitive to mu. That's the first thing. Now, of course, if you crank mu to 10 to the 8, then you might start getting something up here. Okay? And if mu is 10 to the minus 8, you might start getting a point down here. But the point is that for this huge range of mu's in the middle, you have a lot of mu's, and you're just tracing out this little tiny thing here. By the way, if you see that, it means you're seeing a problem where there's not that much trade-off. The two objectives are not particularly competing in this case. That's kind of the idea. Okay, let's do the other one now. Let's do this one. That's J1, J2. Honestly, I don't know why I drew it with J1 vertical, but anyway. All right, let's do the other one, where there's a strong trade-off. So here's the curve, like that. Now, let's talk about minimizing a weighted sum. What happens now? How sensitive, what happens as you vary mu and minimize a weighted sum objective? What happens? It's very sensitive. Okay, so basically for mu below some number, you kind of get points here. Let's say it flattens out over here, something like that, right? For mu above some number, you start getting points over here. Right when mu is around this slope, x of mu, right as you sweep mu through that point, this thing jumps tremendously. Everybody see that? And that's the point here. Okay. This also, you will see this, and it has a meaning. This is the meaning. Okay. And it has a meaning. It means you got a linear trade-off. If the trade-off in here were exactly linear, you'd actually get an amazing thing where, with a weighted sum objective, it would jump from this point all the way to that point with nothing in between. Just be absolutely discontinuous. Okay? Actually, for quadratic functions like we're looking at, that can't happen. But that could happen. Okay, make sense? Now, by the way, when you get many dimensions, all of these things, you can get all of these phenomena. That's the weird part. You can get kind of parts where this surface has got, it's kind of angled. You can get other parts where it's very flat. And as you mess with weights, things will jump from one place to another. Other regions where you mess with the weights. And this, in that case, it's a tangent hyperplane touching this optimal trade-off surface. You mess with the normal. That's what you're doing when you're messing with weights. And it kind of rolls around, doesn't do very much, right? So you can get all of these kind of phenomena, but they're it's important to understand these ideas. Okay. Now let's talk about how you would specifically do this for a least squares problem, a bi-objective least squares problem. Well, how do you minimize this? Well, the way we can take two quadratic objectives and make it, we can just reduce it to a problem we've already solved, is all we have to do is this, is say that the sum of this norm squared plus that norm squared is just this. It's absolutely nothing more. You can check. The top part of this is ax minus y. The bottom part is square root mu fx minus square root mu g. Now the norm squared of a stacked vector is the norm squared of the top plus the norm squared of the bottom. Norm squared of the top is that term. Norm squared of the bottom is that. If you like, you can put square root mu in both of these places, but when you square it and pull it outside, it looks like that. Okay? So that means, actually, we're done. We already know how to, because this we know how to do. This is no problem, right? We'll call that a tilde or something like that. And by the way, it just means that, for example, in MATLAB, it's even simpler. It's something like, a, and if you really even want to do this, something like that, times f. I hope I'm doing this right. And then backslash, and then y, and square root mu times g. Okay? So there you go. There's the code for it. Oh, you shouldn't have to write that down. I mean, but that's it. Okay. Now the formula for it is this. It's, if you take out, it's going to be, of course, it's a tilde transpose a, quantity inverse times a tilde transpose. Well, a tilde transpose a, you can work out analytically what that is. That's it. That's a tilde transpose a tilde, like that. And you see something actually quite beautiful here. You see a transpose a plus mu f transpose f. And that's how this works. And over here you get a transpose y plus mu f transpose g. So it just sort of works out. It's a very pretty formula. Let's look at some examples just to see how this works. I mean, these are going to be really simple examples, but just to see what happens. So this is our friend, the unitless mass on a frictionless table. We have a 10-second period. We apply forces x1 through x10, each one for a second in turn. Okay? And we're just going to have one. We only care about one. We don't care about the velocity. We care about the position at t equals 10. And so we have y equals a transpose x, where a is an R10. And I think we even remember, you may remember what a is. It's, I don't know, I think that it goes down by 1. It's large for the first one and then goes down to a half or something. By the way, when you see vehicle or object motion problems, where the person specifying the problem tells you where this object has to be, but doesn't seem to care how fast it's going, generally speaking, that corresponds to a non-positive social use. Because, I mean, usually this would be something like a missile hitting something. Okay? So you can, when someone says, no, I'd like you to be, if you say, what about the velocity? You go, doesn't matter. You should be suspicious at that point. So, okay. So this is one of those cases where there are no specifications about the velocity of this mass. So no specifications on the velocity. It just has, here you just want to be near the point 1. Now we can, I mean, this is a stupid problem. We could solve it by hand. It's totally idiotic. But just to give you a rough idea, we could work out what this is. J2 is the sum of the squares of the forces used. So this has units of, well, newtons squared. Okay? Oh, and you might ask, why would you care about the sum of the squares of the forces applied? Let me ask that question. Many people, there's whole courses here where the entire course, everything is quadratic. You go take a control course in AeroAstro, everything. Squared newtons, integrated, that's all you see. Why do you care about it? What's that? It corresponds to energy. That's okay. Now I'm going to tell you something. That's not true. That's what they tell you in those classes. That's what I should be telling you now. That's the party line. That's what we're supposed to say. That it corresponds to energy. That's total nonsense. Generally speaking, I know of almost no case where it actually corresponds to energy. And by the way, any case where it does correspond to energy, like in a disk drive servo, there's actually no limit on energy and no one really cares. So, okay, there. I said it. I'm being honest. Now I'll tell you, now, why do you really care? I mean, why do we work with the sum of the squares? What do you think? Thank you. It's easy to analyze. Right, because we can. So that's why. I just wanted to be clear on this, okay? There are lots of other things here. If this was a thruster, you would probably care. That's something you'd really care about. That's the fuel use. That's fuel use. You might care about this. That's the maximum force applied. Why? Because this dictates how big a thruster you have to get. That's actually, this has practical use. This one, the sum of the squares, it might, but it's very unlikely. So you never get an actuator. I mean, then this comes up in signal processing too, and where it says, here it is, needs 28 volts and 5 amps. It says, and it never says under no circumstances should the norm of the input exceed this. That you just won't see that. That's not what it is. All right. So there, I said it. It's honest. But now we're going to go back. Now that I've said that we do this because we can. That's why. Okay. So let's go back. Oh, but if anyone asks you and you don't want to get into this big argument, you just say it represents energy. And if they buy it, move on quickly. That's my recommendation. Okay? All right. So we're going to form a weighted sum of, and I mean, it's kind of a stupid problem. So let's talk about some things here that we can just know immediately. This says that basically you're going to apply a force for 10 seconds. You're going to move this mass, and you'll be charged. There are two things you care about: how much you miss being displaced 1 meter, and the sum of the squares. So let me ask them some questions. Does it make any sense to move the mass like backwards before moving it forwards? Well, obviously not, because you're running up a J2 bill, and not for any particularly good reason in terms of J1. Does it make sense to overshoot the target, which is 1 point, and to say, oh, here's my masses, and say, oh, look at that, my final position was 1.1. I overshot. No, that's totally idiotic, because you'll run up a bill here for overshooting, and it's stupid because for the same amount, you actually could have just landed right at the point and run up 0 bill here. Okay? So you're going to always undershoot. And in fact, you can also figure out in this problem, you're always going to push. I mean, you're always going to push and you're going to push more at first because it's more efficient and blah, blah, blah. So, I mean, you can figure out a lot of this before you ever even form a formula. So the optimal x is this. Now that's a function of mu. That's that trade-off parameter. As we vary mu, we're going to get different full trajectories. By the way, you can even work out an analytic formula for this. That's not the point, and it doesn't really matter. Here's the optimal trade-off curve. So there it is. It's very, very pretty. Here's the energy. Notice how I just said that without making any apology. Here's the energy, and here is the square of the missing distance. This curve actually hits 0 at a point. It doesn't approach 0 asymptotically. It hits it. This is a very interesting point that we're going to discuss either later today or maybe Tuesday. Very interesting point. At this point, you are hitting the target exactly, and you're using the minimum energy possible. That's what it means to say that this curve hits this line. So 0 means y is 1. At 10 seconds, that mass is exactly at a position of 1. That's the energy bill you run up. There are many, many energy force programs that will displace the mass 1 meter after 10 seconds. Many. They all lie along this line, and they're characterized by using more energy. Okay? So this is going to be the least energy thing that gets you right there. Now, what about here? Does this curve hit, or is this asymptotic? Does it hit it? Well, let's ask the question. Would it be possible to run up a bill, J2 of 0? What? Could you? It doesn't move. So you could do that. You could just have x equals 0. So you do nothing. Okay? You're doing very well in terms of J2. You couldn't do any better. Okay? And you just take the hit, which is the cost on J1, and that's here. By the way, this is a beautiful example. Take a look at what that curve looks like near 0. So basically, someone comes to you and says, I'm sorry, no, it's just I'm just not going to do anything. This curve is, not only does it have a steep slope, it has infinite slope there. So that says that with extremely small levels of force applied, you can reduce your mishit distance by a correspondingly very large amount. Okay? So that's the picture. I mean, this is a silly example, right? I mean, you could have done all this analytically or figured it all out, and there's no surprises here. Trust me. If this was a vehicle with 12 states and 13 different inputs representing different thrusters and control surfaces you can actuate and things like that, this is not obvious. You already have like 5 lines of code that will beat anything any person could ever come up with, ever. And I'm talking about like good pilots and things like that. Okay, so same code, 3 lines. I think it's just the one I wrote before. It's not even 3. 3 with a lot of comments, actually. Okay. So this stuff looks simple. This example is stupid. Trust me, even if these matrices, if the dimensions of vectors get to be 5, 10, let alone 500 or 1,000, you're doing stuff that is absolutely impossible for someone doing, intuitive-based stuff to even come close to. Okay. Now, there's a very famous special case of bijective least squares. Very famous. And it's this. It's where the second objective is really simple. It's just a norm squared. And so here, the way to understand the semantics of it is you have a problem where you say, I want a good fit. I want ax minus y norm squared to be small. But I don't want to do it if the only way to do that is to have a giant x. So I want some trade-off there. I will accept a poorer fit in return for a modest x. Now, how you set where you operate on that curve, that determines the trade-off of the optimal size of x versus the fit. At least one end of the trade, we actually know a couple ends of the trade-off. When you only care about J1, that's just least squares. That's classic least squares. We know the solution, everything. If you only cared about J2, let's get that out of the way right now. If you only cared about J2, what's the best choice of x? 0. Okay, and the objective on the other side? Norm y squared. So the 2 endpoints of this trade-off curve are now known. By the way, that's an exercise you should always do, is figure out what you can say about the endpoints, because all the action then goes down in between the 2. Okay, now in this case, you get x is A transpose A plus mu I inverse A transpose y. It's got lots of names. Maybe the most common is Tikhonov regularization. In statistics, you will hear the following phrase. There's probably many others. In statistics, this is called ridge regression, and mu is called the ridge parameter. In Tikhonov regularization, mu is called the regularization parameter. Now I'll show you something kind of cool about this. That's this. This formula makes sense for any A. Skinny, fat, full rank, not full rank. Okay? Now I have to kind of justify that probably, and so I'm going to. So here's my claim. My claim is that A transpose A, there's lots of ways to prove this, but I'll do one. I'm going to claim that I want to say that's invertible, provided only that mu is positive. And this formula even makes sense for A equals 0. It's a stupid formula, but it makes perfect sense. I'm saying provided here mu is positive, right? So if A is 0, it's no problem. It's x equals, mu I inverse. Mu I is perfectly invertible times 0, so x is 0 in that case. Okay? So by the way, when mu is 0, you recover least squares. And now this formula is one you better watch out for, because that formula only makes sense when A is skinny and full rank. Okay? It parses, but it doesn't pass a semantics test if, for example, A is fat. The weird thing is, you can do Tikhonov regularization if A is fat, and this makes perfect sense. Or at least I'm going to show that in a minute. Everybody see what I'm saying here? By the way, this is why some people use Tikhonov regularization. Because they're lazy. Or they tried this, and they got some error or something somewhere. Some software told them that they were trying to invert something that was singular to working precision. And they were like, oh, whatever. And then they just put in plus, 1e minus 6i. And they said, now it's working. So, no, trust me, you see a lot of that. But let me justify why this is, that this matrix here is in fact invertible if provided mu is positive. And totally irrespective of A. I don't care about the size of A, I don't care about the values, rank, couldn't care less. Let's check. So what we have to do is we have to do it in a thought experiment, and you say, well, look, that's a square matrix. Suppose it were singular. That means there's some vector z which gets mapped to 0, and z is non-zero. That's what it means. It means this matrix here, because it's square, being singular means it's got an element in the null space. It's non-zero. Okay, so that's the case. All right. Well, let's do something here. If this is the case, I'm going to multiply that equation on the left by A transpose, and I'm going to write this down. Well, that's surely 0, and that's 0. This is the 0 vector. That's 0 number. Why? Because z transpose times the 0 vector is 0, obviously. Okay. Now what I'm going to do is I'm going to take this and let's expand it. I'm going to write it this way. I'm just going slow here. Plus mu, and I'm going to I've commuted the mu, and I get that. Okay. And now I'm going to write this as norm az squared plus mu norm z squared equals 0. And now I'm going to use a very, very deep mathematical fact. Ready for this? If you have a sum of two non-negative numbers and the sum is 0, you can make an amazing conclusion. That is that both the numbers are 0. Everybody follow me? So norm az squared is 0, so norm az is 0, and norm z is 0. Okay? Oh, by the way, this, if you want to know where does the mu positive come in, it's right now. Because if mu is 0, I can't assert, all I can say is that. Okay? So this says because this is not 0 up here, right? We have our contradiction and we're done. Okay? So that's why this works. That's one way to say it. Another way to say it is to look at this stacked matrix and just show that the stacked matrix is that this stacked matrix, F is I, is full rank. That's the other way to look at it. And that if you take any old matrix at all, any size, any shape, any values, and you stick below it square root mu, a positive number times the identity, that matrix is full rank, period, and skinny. So period. So that's the other way to think of it, which is also probably a better way. Okay. So this is called Tikhonov regularization, and it has lots of applications. So here are the types of applications you would see. It's very common in estimation and inversion, and it works this way. So typically something like ax minus y is a sensor residual. So here, if you just blindly, if you choose the x that minimizes the sensor residual, you know, fine. And by the way, and you like the x you see, great, no problem. But in fact, you might have some prior information that x is small. If you have prior information that x is small, or another application is where is actually your model y is ax is actually only approximately valid, and it's certainly only valid for x small. We're going to see an example of that momentarily. So the regularized solution trades off sensor fit and the size of x. So that's what you do. Okay, and and this, by the way, this comes up in all sorts of, it comes up in control, estimation, communications, blah, blah, blah. And it's always the same story. There'll be some parameter in some method, algorithm, something like that. And when you turn this knob, because that's really what mu is, it's a knob, that basically tunes your interest. Actually, it tunes your irritation, is what it really does. It tells the algorithm what you're more irritated by. As you turn mu, what will happen is at first you'll get, you know, if you turn it all the way one way, you'll get a control system that's kind of very, very slow and, you know, doesn't do such a great job, but it doesn't use huge forces, right? You turn the knob all the way the other way, and you'll get something that's very snappy and is using very big forces or things like that. In communications, you get something that equalizes things out beautifully, but it's very sensitive to noise. You turn the parameter the other way around, you get something that is going to be really, it's kind of very calm, doesn't overreact to any like noise or anything like that, doesn't equalize things, you know, it cleans it up a little bit, not much. And so these are the types of things. You'll see these all over the place. Let me mention some examples in image processing. That's a very famous one. And this should almost really, we should actually add that to the notes. So very famous one in image processing is this. It's called Laplacian. Okay, here we go. Okay, it's Laplacian regularization. So let me say what that is. You've already done one, or you will by 5 p.m. today, looked at an image reconstruction problem. Now in that image reconstruction problem, the sensor measurements are pretty good, and there's not going to be, there won't be any problem. It'll just work. Why? Because we arranged it to. Okay? However, in general, you'll have the same sort of thing. And actually, what you want to do there is you want to add, so let me just explain what we're doing. I want to estimate an image. So I have an image here, and I have some pixels. These could be voxels. I mean, I don't really care, like this. And what I'm estimating, my x, is sort of the value in each of these things. Now, if with your sensors you estimate x and you get some crazy numbers that are, that vary pixel by pixel by huge amounts, this is kind of hints trouble, because normally when a person writes down pixels, there's sort of an implicit assumption that you're sampling fine enough. Okay? So for example, if this were, well, I don't know, if this were like, plus 10 and that was minus 30 and there were wild swings here, what you'd do when you looked at that is you'd probably say, you need to sample finer, is probably what you would say. Okay? Okay, so now my question is, let's say that ax minus y. X is a vectorized version. It's a rasterized version of the image. So this is going to be sort of misfit from my sensor readings. I want the following, though. I want to trade off the fit, that's this thing, with the smoothness of the image. And now I'm waiting for you to tell me, what do I do? Here's a hint. Let's add a new objective. To do this, we have to add a new objective. And the new objective is going to be it's not smoothness, actually, it's the roughness. So we have to write down a roughness objective. Someone please suggest a roughness objective, which is kind of a norm. You have one? Perfect. Okay? So we're going to form a vector, which is the difference between neighboring pixels. Okay? It could be, we could have vertical or horizontal. We could have diagonal. It doesn't matter. We could have all of them. So I'll skip a few details here. They're not that complicated. When you do that, you can actually write that as, I'll call it a matrix R. No, you know what I'm going to call it? I'm going to call it a matrix D, because it's really a differentiation. And I'll take dx, and I could have things like d horizontal and d vertical x. Okay? So this is a new image whose value at a certain pixel is the horizontal difference here, and that's the vertical difference. By the way, if both of these matrices, describe the null space actually of these two matrices. What's the null space of these two? Constant. Not all, yes, all ones is in it. But in fact, this would be any image that is constant along horizontal lines, but it can vary in x. The null space of this one would be any image which is constant along vertical lines, but can vary this way. I don't know if I got that right. I think I did. Something like that. Okay. And, okay, so what you do is simply this. Ready? And we're done. There. That's a least squares problem. Now you tune mu. You turn mu all the way to 0, you get the problem you're doing now. You get no regularization. In other words, if you like what you see, in this case, there's no problem. If, however, you do this, by the way, in many problems with noise and things like that, when you actually just minimize this, you'll get an image which is way too wiggly and stuff like that. Now you turn mu up. By the way, if you turn mu all the way up, like way high, what does the solution of this look like? Don't do the math. I just want the intuition. Yeah, it's totally smeared out. It's just like it's a big gray mess. and it's just equal to the average value or something like that, right? So somewhere with mu in between, you're going to see the right picture. And then you might ask, you know, how do people choose the regularization? Everyone see what I'm saying? This is how you use regularization. This is it. I don't know why we don't have an example of that in the notes. We'll add one, I guess. So then there's the question of how do you choose mu? So how do people choose mu? We should distinguish two things. How do they really choose mu? And then when someone asks them, how do they choose mu? What do they do? Yeah, so how do they really do it? They try this for one mu and they go, no, it's too smeared out. Reduce mu. And they go, nah, it's getting too much speckle in there from the, I can still see some weird artifacts. And they go, increase mu. So they iterate over mu. They're just tweaking mu, playing with it. That's how they really do it. Okay? Now, what happens if someone says, in like a formal design review, how did you choose mu? Then they go, well, you know, I calculated this optimal trade-off curve, and statistically this corresponds to the posterior variance of this, that, and the other thing, and I used a such and such model, and that's how I came up with mu equals 2 times 10 to the minus 3. Okay, that's what they would say. Whereas in fact they tried mu equals 0.1. That was too much. It got too smeared out, and they tried mu equals 1e minus 6, and it wasn't. They didn't get enough regularization. So that's how they really did it. Okay. Any questions about this? So, by the way, if you know about least squares and regularization and tricks like this, you're actually on your way to. I mean, this can be very effective in a lot of problems. Yeah. Oh, by the way, one more point about this. If you go back down to the pad here. This penalizes smoothness, but suppose you also care about the size of x. Suppose you run this, but x is like huge. It's smooth but huge. How would you also deal with this? How would you rein in the size? I'll take my pen out. What do? You got it. Plus lambda norm x squared. Okay. How would you choose lambda? By messing around. How would you say you chose lambda? You would talk about the optimal trade-off surface and tangent and exchange rates, and then if you've had some statistics, you could throw in some statistical justification. But you found it by fiddling with it. Oh, it's not just total fiddling with it. As you increase lambda, you can say one thing about the image. What happens? It gets smaller. And it's going to be a little bit rougher, and it's going to have a little bit of a worse fit to the measurements, if that's what these are. Okay? That's it. So now you know how regularization works. It works quite well. Okay. Next topic is related. It's also a huge topic. Nonlinear least squares, NLLS. And here it is. It says, I have a bunch of functions. Now, for us, we have the residuals is ax minus y. That's an affine function. It's linear plus a constant. Okay? And what we do in least squares is we minimize the sum of the squares of the components of the residual. But now the question, what if these ri's are non-affine? That's the general case. And this is called the nonlinear least squares problem. I mean, actually, of course, this residual is not linear either. It's affine. But linear sometimes means affine. Okay. So how do you solve a problem like that? Well, we'll get to that in a minute, but let's just look at some examples. These come up all the time, nonlinear least squares. So here's a perfect example is GPS type problems where you have ranges. So you have measured ranges, and from that you want to estimate where a point is. And so there you don't have to linearize, you would just minimize. This is actually now the range error, exact range error squared. This comes up in tons of places. In estimation problems, it would come up because you have some kind of nonlinear sensor. Instead of something like a line integral through something, you might have something that is nonlinear. This comes up all the time. So that's an example. Now, how do you solve these problems? And here, I have to tell you something. And the first thing that has to be admitted, if we're being honest, I mean, there's nothing that great about being honest, but to be totally honest, no one can actually solve this problem in general. So that's the truth. Is basically this problem cannot be solved. Okay? So instead, we have heuristics that solve this problem. And solve, you didn't catch how I pronounced it. They don't really solve it. That would be they solve it like that. Okay? So you don't actually really solve. So nonlinear least squares problems in general are not solved, period. Now if you go to Wikipedia, if you go to Google and type in nonlinear least squares, whole books, everything, all over the place, you will probably find nothing that admits this fact. Now that's a very big difference from linear least squares, or least squares that we've been looking at. So far, when we said that A transpose A inverse A transpose Y is the least squares solution, we weren't lying. That vector minimizes the norm of R if R is AX minus Y. Absolutely. No, there's no fine print, nothing. That's the minimizer. All methods for nonlinear least squares problems don't have that property. They are all heuristics. Okay? But you probably won't find out, and certainly from people who are giving you who have an algorithm for this. People will give you soft. And it gets kind of weird after a while to say things like, how'd you do that? So after a while, in slang, you say, I solved the nonlinear least squares problem. Technically, that is false. You'll see that in papers. It's false. When someone says that in a paper, there's always the question, because there's two options. Either A, they know they haven't solved it, and they're a liar, because they're saying in a paper they've solved it, or B, they don't even know that they may not have solved the problem. It's usually the latter. That's usually the problem. Okay? They're just total clueless. They're like, I don't know, I got the software, I downloaded it from the web, I typed make. It was called nonlinear least squares. It didn't complain. So, but you have to know it's all a heuristic. You don't get the answer. By the way, in practice, you very often do get the answer, but you don't know that you got the answer. So, all right. I made enough of a point about that. Having said all that, and also having said that I will probably slip into language, the informal language, where I'll say, how do you solve nonlinear least squares problems? You don't. The answer is you don't, because you can't, because no one knows how to do it in general. How do you approximately solve, or something like that? So you have to put a qualifier, like maybe an asterisk, and then at the bottom of all these pages you just have a little note. It says, where it says solve, and then down here, I'll just write it in just so we're all cool here. It says, not really. Or sorry, but maybe, right? But maybe. Okay? That would be the right thing. And then we'll just put, that's just in force until I say it's not. Okay? So how do you solve least squares problems? There's lots of methods that are heuristics, and they often do a very good job for whatever application you're doing. Okay, so the very, very famous one is Gauss-Newton. By the way, the name of the method suggests that this was not developed 5 years ago. This is not exactly a new method. And it's actually pretty straightforward. It goes like this. You start with you have a starting guess for x. And what you do is you linearize R near the current guess. Now linearize means find an affine approximation of R near there. Then what you do is you replace that nonlinear function with this affine one. Affine least squares, which on the streets is called linear least squares. We know how to do that. That's what we've been doing for 3 days. Okay, so nope, that's no problem. Then you update, that's the new x, and then you repeat. So you get a different model. So this is called the Gauss-Newton method. And here's some more detail, and here's the way it works, is you take the current residual, and you form, basically what you're doing is you form an approximation that says if x were to be near xk, then I would have r of x is about equal to r of xk plus, that's the Jacobian, times the deviation. Okay? And then here, if you wanted to, you could say something like ' provided something like x is near xk. Okay? So I could put a little comment there like that. Okay. Now now what we do is we write down the linearized approximation. We rewrite this to make it look like well, it is an affine function, but we can put it like this. It doesn't really matter. Now what you do is you minimize the sum of the squares of these things over choice of x. Okay? And that gives you your next iterate. Okay? So that's the next iterate is that. And it's just a formula for that, which is this thing. Now, and you repeat until this converges, which, by the way, it need not. Okay? There's a question? Yep. Absolutely. You're right. And I'm very glad you brought that up. So the question was this, that last lecture I believe I was ranting and raving about calculus versus least squares, where calculus is getting a linear model of something that's super duper accurate right near the point. But it's vague about the range over which did you notice that in your calculus class? Like, they go, this is a really good estimate near this thing. And you go, well, what does near mean? And they're like, just, near. Don't you, that's the beauty of all this, right? I don't have to say how near it is. It's like the limit. Anyway, so, all right. So the point was, how about doing Gauss-Newton, where you don't use the derivative, the Jacobian, but you get a least squares based model. Uh-oh, I lost it. A least squares based model. Here it is. It's hidden. Instead of this, use a least squares based model. And that was your question. And I can tell you this. That is an outstanding method, often far superior to Gauss-Newton. So so my answer to your question is yes, that's a good idea. And often works really well. And in fact, there's a name for this when in the context of filtering, when you're doing estimation in a dynamic system, that's called a particle filter. And so let me just say a little bit about that. So this, by the way, I had some pseudocode here that was, here we go. So at this level, it's so vague that the linearized near current guess, you could use several methods there. One would be calculus, and the one I just described is calculus. But in fact, linearized near current guess, that could be done by a least squares fit, just as you recommend. And you wouldn't call this Gauss-Newton anymore, but you might or something. Anyway, in the context of filtering, it's called a particle filter. These work unbelievably well. And the way you would get, instead of this thing, which is sort of calculus, what you would do instead is you'd take xk and you'd add to xk little perturbations. And you'd actually evaluate r of xk for a whole bunch of points right around there. And then you'd fit the best affine model to what you got. And then all the method would work the same. And that would work really well, by the way. So, okay. All right. Oh, by the way, one little comment here. This says provided x is near xk. So you could well get into trouble here because you linearize. In this case, we did it by calculus. You linearize, and at least it says if x stays near xk, this is a good model. But then you just solve this problem, and there's no reason to believe that this point is near xk. If it's not near xk, then the whole premise for how you got xk plus 1 is in doubt because you're using this model, which need not be valid. So there's a very cool trick, which since we just did regularization, I can tell you what it is. The super cool trick is this. You add this. There you go. This says minimize the sum of the squares of my model for the residual. That's what this says. This says, but please don't go very far from where you are now. Because if you do, there's no reason to believe that's a good model. And by the way, this is sometimes called a trust region term. That's a trust region term. Because when you form this model, by the way, either way, either with least squares or with calculus, you have the idea of what is the area around xk where you trust that model. That's the trust region. And this basically is your trust region term. Everybody got this? So once you know about regularization, you start realizing you should be using it kind of in a lot of places. And this would be a perfect example. But what I described here was sort of the pure Gauss-Newton. Let's look at an example and see how this works. So here's an example. We have 10 beacons. No linearization here, at least not in the main problem. Now the true position, that's this point right here. And that's where we started off. And let me tell you what the measurements are. At each step, I'm going to get 10 sorry, take that back. I have 10 measurements, not at each step. I have 10 measurements. What I know is the distance of a point to each of these beacons. These are noisy. By the way, if they were noise-free, this problem would be trivial. If they were noise-free, if I knew the range to this point, I would draw a circle with that radius around that point. I would do that for all the points, and they would all intersect in one point, and I'd say that's where you are. The problem is the range measurements have errors. Okay? In fact, they're considerable errors. They're like plus minus 0.5. So they're not really going to all they're not all going to come to one single point. Okay, and we'll use Gauss-Newton for that. Actually, here it'd be there's other methods you could use, but this is just a simple example. By the way, this is what the least squares, the nonlinear least squares objective looks like as you vary x. This is going to be, that happens to be the true global solution in this problem. But you see, this is not a quadratic function. I mean, which would be a nice smooth bowl. It's got all these horrible little bumps and things like that. By the way, in this problem, it doesn't have any local minima that are not global. But we could easily have done that by putting some point here, and then there would have had a little valley here that would have filled up with a lake or something. As soon as you have that, I guarantee you Gauss-Newton method will, given the wrong initial point, land right there very happily. At which point, you have not solved the problem, and you don't know it. Okay? Okay. Well, if you run Gauss-Newton on this, starting from here, and you're way, way far away, in this case, it actually works. In the sense you actually do compute the solution, but you don't know it. I only know it because I plotted it. It's got 2 variables, and I plotted it over for everything. But the minute you got 5 variables, you're not going to know it anyway. Okay? So what happens now is the objective in the Gauss-Newton iterate just keeps going down. And you can see that in about 5 steps, it hits what appears to be a minimum. And it takes maybe 5, 6 steps or something like that. And that's it. Now, by the way, you don't really know. The final estimate, by the way, was quite good. The final estimate's minus 3.3 plus 3.3. So that's the actual true position. That's where you started. After 1 step, you were here, and 2, you were here. Then there, then there. And now you can see you're sort of in the region where you're going to get the answer. By the way, it's pretty good. You are getting, from the least squares part of it, you are actually getting the blending of 10 sensor measurements. So you're getting the power of blending. So actually, some people call that like a blending gain or something like that. And I guess I forget what they call it in GPS. They have some beautiful, colorful word for blending lots of sensors, measurements, and then actually ending up with an estimate that's better than any of the individual sensors. So same sort of thing. So here you actually end up with an unusually good estimate, better actually than the accuracy of your individual sensors. So that's the picture. Now in this case it actually worked. In other words, we got the global solution, but that's only because I plotted it. I think I already mentioned this. But let me ask, well, I can ask you. Suppose you have a problem. Real problems don't have 2 variables, I might add, right? You have 2 variables, you plot it and use your eyeball. Okay, so this is silly. You have 3, you write 3 for loops and you go to lunch. Okay, so let's just bear that in mind. Real problems have 10 variables, 100, 1,000. Okay, you cannot plot pictures like that. So you have a nonlinear least squares problem where you are estimating, oh, let's say you have some nonlinear estimate, maybe it's some tomography thing. So you have a nonlinear sensor. It's a variation on the problem you're doing for homework right now. Except instead of having a linear sensor, you have a nonlinear one. Okay? And so you're going to do nonlinear least squares. How big is that problem we gave you? I don't know, how big is that image? Like 30 by 30? Tiny. Okay, but 30 by 30, what is it, 30 by 30? Okay, so that's 900 variables. That's pretty small. Now you run a Gauss-Newton in 900 variables, and you get an image. By the way, if you were imaging somebody's head and it came out looking like a head, that's good. I mean, that would be your feedback that something is approximate. If it came out not looking like a head, that wouldn't be good. So actually, what do you imagine? What do you think? What would you do as a practical matter there to check whether you got, in fact, or just to enhance your confidence that you may have actually minimized the nonlinear least squares? What would you do? You'd what? Exactly. You'd run it once, and you'd see what you got. Okay? By the way, if you had a pretty good estimate ahead of time, and it's like that's actually likely to help. You start with that. But what you might do is exactly what was just suggested. You run it multiple times from different starting points, and you just see what happens. And here are some of the things that can happen. The first is that no matter where you start it from, it always goes back to the same thing. Okay? And what do you know if you do that 50 times? What do you know? Well, let's be very careful in our verbs. I use the word know. So what do you know when you run it 50 times and you keep getting the same point? Here's what you know. I will summarize it. Ready? You know nothing. Absolutely nothing. And I mean both in theory and in practice, you know absolutely nothing. Because R900 is a huge place. Huge. And it's absolutely, and the fact that you just sampled 50 points out of it, that's nothing. So you know nothing. Now, as a practical matter, what can you say when someone says to you, I did the imaging, there it is, I believe that's the image. It looks good. It's clearly it's a head, and there's somebody's brain there, looks good. But someone says, do you know that's the global minimum? And you go, no. But I tell you what I did do. Last night, when I went home, I started up a batch of doing 1,000 of these from different initial conditions. And I found that in something like, let's suppose you found in all of them, you say, in every single case, I converged to the exact same final estimate. And they go, cool, you're getting the global minimum. If there's no lawyers present, you can say, good bet. But if there's any, but other than that, if someone really says, what can you really say you can't say anything. You can say, I don't know. So you would say if you ran 50 and got the same answer each time, you'd say that as a practical matter, you have enhanced your confidence in the design. And actually, I'll tell you, there's a great phrase which makes absolutely no sense and is wrong. It's very useful, therefore. It's this. You can say exhaustive simulation. Have you heard this phrase? That's great. So this is what you say to someone when you open the door and you say, hop in. And you go, are you sure this works? You go, oh, no problem. We used exhaustive simulation. Hop in. Okay? So that's a very useful phrase. Of course, it makes absolutely no sense if there's more than like 3 or 4 things varying, and is generally speaking just wrong, right? If you check you say, oh man, we checked 1,000,000 values of bursts of wind and things like that, all sorts of terrible things. We've simulated them all. Well, of course you cannot. So that's useful. If you find yourself in a situation, you can always use that phrase. And then you mention the number, and as long as this person doesn't take the nth root of that number, where n is the number of parameters, everything is cool, right? Because 1,000,000 simulations in R10 is like 0. It's like, the 10th root of 1,000,000, which is a small number. Okay, so that's nonlinear least squares. I hope we have a problem on that, but I have this weird feeling we didn't. We really didn't. It just didn't make it, huh? That's horrible. Well, fortunately, we have some recourse, don't we? Oh, okay. So it seems that over the next week, you might not see nonlinear least squares. So, but it's an important topic, and really one that should be covered in the first half of the course. And I mean covered like I think you should do one. So, okay. Let's look at the next topic. I'll just say a little bit about the beginning of the topic. It's essentially the dual of least squares. So, and you'll get used to this idea of duality. Later it'll get, no, actually I don't think we'll ever get very formal about it. But at least I give you the rough idea. So let me say a little bit about duality. It's going to involve ideas like this. It's going to involve transposes. So there's going to be transposes. Rows are going to become columns and things like that. Null spaces are going to become ranges, and that's the kind of thing. By the way, there's a duality between sort of control and design and things like that, and estimation, right? Because there you're switching the roles of x and y, typically. So these are all sort of the ideas. We've done least squares so far. The dual of that, or a dual of that, is going to be least norm solutions of underdetermined equations, because we've so far been looking at overdetermined equations. And we'll see what this is. I mean, this is actually, it's actually pretty straightforward stuff. So now we're going to take y equals ax, but a is fat now. Now, that means m, you got fewer equations than you have variables. That's right, so you have more variables than equations. So another way to say this is x is underspecified. So even if there is, if there is one solution here, there's going to be lots, because you can add anything in the null space of A, which, by the way, has to be more than just the 0 element now, because it's got a dimension at least n minus m here. So we'll assume A is full rank. So that means that you have m equations, and they're actually independent equations. So the rows of A are independent. Then all solutions look like this. The set of all x's that satisfy ax equals y is you find any particular solution here. You will very shortly see a particular solution, a formula for one. You take any particular solution and you add anything in the null space. Okay? By the way, if a person chooses a different xp here, you get the same set, because the difference of any two solutions is in the null space, and you get the same thing. Okay. So here in this description, z essentially parameterizes the available choices in the solution of y equals ax. And you can say roughly that the dimension of the null space of A, which is n minus m because A is full rank, that gives you the degrees of freedom. And that says you can choose x to satisfy other specs or optimize among solutions. Now, I guess as we talked about before, as to whether or not that's a good or bad thing, that depends on the problem. If this is an estimation problem, degrees of freedom are not good. Basically, that's stuff you don't know and cannot know with the measurements you have. If this is a design problem, this is good, because it means you can do exactly what you want many ways, and therefore you can choose a way that's to your liking. Okay, so that's the idea. Okay, well, I might as well just show this, and then we'll continue next time. Here is a particular solution. It's A transpose times AA transpose inverse times y. Boy, should look very familiar, but be a little bit off. You are used to A transpose A inverse A transpose y. You're used to that formula. And this looks very different. It's a rearrangement of move a few things around. They looks perfectly fine. You have to be very, very careful here, because it's very easy to write down things like that and that. What you must do, and I'll show you my mnemonic. My mnemonic is this. You look at that, and you look at that, and you quickly do the syntax check. The syntax scan goes like this. If you saw A inverse, your syntax alarm would go off, unless you know A is square. But here, A transpose A, that's square, and therefore, at least by syntax, can be passed to the inversion function. That's cool. And in fact, you can check that you can multiply by A transpose on the right. You can also form AA transpose, and that's invertible too. So syntactically, this one is cool too. However, so both of these pass the syntax test regardless of the size of A, fat or skinny. Now let's get this to the semantics test. So now if A is fat, then this one is basically a fat times a tall matrix. And the result is you get a little one. Okay? Over here, if A is skinny, this is also a fat times a tall, and the result is a little one. So here's the semantic pass. The semantic pass says if you propose to invert a fat times a tall matrix, at least unless there's something else going on, like some rank condition, you're not in trouble yet. If these two reverse, you're in trouble independent of what the entries of A are. Because if you reverse these, if A is fat and you go to this formula, that is a square matrix. That's fine by syntax. It fails on semantics because A transpose A is going to be it's square, but it is low rank, and you should not invert low rank matrices. Okay? So I guess we're over. So we'll quit here and continue next week.